All right, so let's go through the different types of discontinuity. So for this first one, this is called a removable discontinuity because you have this hole in the graph and the location is always x equals. You're talking about where it's going to be located at. And so keep in mind that removable is the open circle. Okay, number 2, this is an infinite because you are looking at a vertical asymptote. So you've got something through here. Notice you've got that vertical asymptote. And so there's that continuous break there. So this is discontinuous, it is infinite, and you do tell us where it's at x equals -2. And then over here with number 3, if you notice that this is continuous, please keep in mind that you don't have to fill in anything else because it is continuous. Just leave all the rest of this blank. Now we had one more type of discontinuity, and that was your jump discontinuity. And that one, it kind of makes sense that it was called a jump just because it looked like you would have to jump from one side of the function to the other to get through it. So that would be a jump there. Okay, whenever we do our end behavior, as you go through this, do make sure that you have x approaches positive infinity and then x approaches negative infinity or vice versa. That's talking about your x-axis, moving along left and moving along right. Now, this other portion, talking about your f of x, that's looking at the very ends of the graph, seeing which way they're going. So for this first one, does it make sense that this is tending toward negative infinity? Well, sure, both the ends are, right? But if we look over here at number 5, again, notice the pattern. You have x is approaching infinity, x is approaching negative infinity. But this time, be careful because we got a number there, -6. As x is moving as far right as it possibly can, notice that the end of the graph is leveling out and running parallel to y equals -6, which, by the way, would be a horizontal asymptote for this. So do be careful there. And then on the next part, again, you're still looking at here as x approaches infinity, left and right. Notice that is the same all the way through. And then for this, notice you've got -1 because as you move to the left or if you move to the right, notice the ends of this is flattening out and going along that horizontal asymptote. So again, this one would imply that you have a horizontal asymptote at y equals -1. So for your even and odd, or no, this is going to be symmetrical, x, y axis or the origin. So a quick review here, looking at this, you can just about identify from the graph that this is going to be symmetric about the y-axis. So that's the only test you really need to go check. If you're checking the y-axis, keep in mind you plug in a -x. Once you simplify, notice that comes back to the original. So this is symmetric about the y-axis. And we can also say, since that's the case, that this is an even function, isn't it? Both of those go hand in hand there. Questions about it? All right, so let's look over the next one. Now, number 8, looking at it, you can tell all 3 of these. We are symmetric about the y-axis. We are symmetric about the x-axis. And even if we rotate 180 degrees, we are still symmetric. So that's the origin. Now, I do want you to check all 3. If it is all 3, do check all 3. However, the only test that I'm asking y'all to show would be from the origin, because the origin is incorporating both the -x and the -y. So there's no sense in repeating that over and over. Okay, now the next part, we're going to talk about even and odd. Now, when you talk about symmetry with even and odd, if you're even function, then you are symmetric with the y-axis. And odd, you would be symmetric with the origin. Please do not say that you're odd and symmetric with the x-axis. If you're symmetric with the x-axis, let's take a parabola, turn on its side here. Notice that is symmetric with the x-axis, but it is no longer a function, is it? So you have to be careful there. Make sure if you're talking about your symmetry, then or even an odd, that your only symmetry would be y-axis and origin. And here, a lot of times we get stuck on substituting in our negative x. Notice that is your first step for all of these. Once you plug in your negative x, here with the odd root, you can have a negative. That is okay with odd roots. No problem with it. You pull that out. Now notice here though, some good questions came up about that's not the original. You are correct, and that would mean this is not even. But to go check the other case with odd, that's where we took the original function and multiplied it by a negative. So if I take this original and multiply it by a negative, notice I get what I had when I substituted in negative x. So when that happens, notice here, that's what's making this odd. And it's also telling you that you are symmetrical about the x-axis. If we look over at number 10, same idea here. You start with substituting in a negative x. That did not generate the original. Now, a lot of people like to say, well, if I multiply the original by a negative, a lot of times kids want to just put that negative right here in front of x. You can't do that. It should be negative times the entire thing. And if you were to distribute that negative, you would get a negative x, but what's going to happen to the 1? It's going to turn to a positive. So you have to be careful with that. That one, again, would be neither. Over here, the last one, number 11, that one's pretty easy to pick out, whether it's going to be even, odd, or neither, simply because of our exponents. It's kind of giving this one away, because if you plug in a negative x and you raise it to those even exponents, you didn't change anything. So that is going to be even. Okay, with our average rate of change, a huge thing for us to remember here, this is not an ordered pair. That is your interval. So in other words, when you break this down, this is the same thing as -2, comma, and you need to find f at -2. And then we have 1 comma, and that's going to be f at 1. And remind yourself this notation means to substitute in, doesn't it? And we have up here our function. So when we sub in, we're going to find f at -2. And you are welcome to type all of that in your calculator. I don't mind. Our goal here is not to see how great we can number crunch. Okay. And if we solve that, it looks like you should get, was it a -3? I think, if you typed it in your calculator. And then if you find f at 1, you again go back and sub in. Minus 7 times 1 plus 3. And then here, that one's going to generate for you 9, I believe. Questions about it? Yes.
Why is there a 5?
Where's there what?
Why is there a +5?
A +5 here? Because I'm on crack.
Okay.
Sorry. Is that okay? Y'all got it? All right. Can you use your slope formula from here? Yep. Y'all know how to do those? What about 13? Are y'all okay with that? Did y'all go sub in? Yes? No? Maybe? No. Nope. All right. So for that one, let's go over to the side. Is the fraction messing you up? Yeah, that's usually going to be like, oh dear goodness, what do they want from us? Or is it simplifying this? Or is it both? Both? All right, so whenever you sub in, this number looks like it's coming from plugging in a -8, I believe. If we plug in that -8, you're going to get 2 times -8 all squared minus 5 over -8 plus 1. Again, you're plugging in the whole thing there. Is that okay? Now, if we multiply this out, that's going to be 64. -8 all squared is positive 64. Times 2 is 128. 128 minus 5 is 123 over -7. So that's where that came from. And then if we plug in -4, then it looks like we're going to get -9. Okay, now to do the other stuff with this, what you're going to need to do here is your slope formula, which is what you're looking at here. And you have your slope formula here. Now let's look at how to reduce that fraction. So what you're going to do, you keep the top. Do y'all remember keep, change, flip? So you keep the top 60 over 7. And then you're going to change your division to multiplication. And then you're going to flip that bottom number. If you're typing it in the calculator, you can go ahead and type in this first fraction here and then do divided by and then type in that bottom fraction or the bottom number and it'll do that for you. It'll calculate it. Here it looks like you're going to end up with 15 over 7. You will have word problems on the quiz that we're taking. But keep in mind, you're not going to have to do anything that we've not already done. Do keep in mind that right here, whenever you have your interval, 1.5 to 2.25, I got that from right here. That's your time interval. You're going to be given some kind of time interval. One of the other problems that we looked at, it said for the first 200 something, if you're looking at the first 200, you're starting at 0 and going all the way to 200. So that's your interval. Now that you have those intervals, notice that you've got to go find the y that goes with it. In order to do that, that's why they've given you this function. That's why it's there. So that you can go plug in. I do expect you to be able to plug it into the calculator. However, if you're not sure about where maybe an exponent key is or something like that, I do want you to ask me. I don't want you to miss it because you were not sure about the calculator. Now, don't ask me, is that the right number to type in? Because then I'm going to look at you and say, I don't know. But if you're like, I don't know where the exponent key is, I don't know where the divide, I don't know where the fraction template is, ask me. I will be happy to help you with those things. Okay, so do make sure you can type in this and this, get those. And then from there, you're doing your slope formula. So again, -13 minus 11 over 2.25 minus 1.5.